Okay, so what we're going to do today is add some more vocabulary and some more theorems. So we talked last about tangents and how every tangent to a circle is going to be perpendicular to a radius. And the idea that there are an infinite number of radii in a circle allow this to happen. Also remember that we did talk about another theorem where we had chords in our circle, and if a diameter was perpendicular to a chord, it would bisect that chord. So perpendicular, excuse me, has a lot to do with our theorems because of that shortest distance between a point and the line. And again, remember me standing in front of the classroom trying to get to the wall, knowing that the fastest path to the wall wasn't going to be some diagonal or some slant other than what would make a perpendicular direction. So we're going to talk about the same thing very quickly right now, and we're going to talk about what happens if two chords are placed in a circle, and we'll call this one BC, we'll call this one XY, and the biggest piece of information that we want to look at right now is they're not at this point radii, but we are going to look at these two segments from A, from our center. And what you're going to notice is that we are also talking about equidistance. We're talking about the fastest path. So if these two segments, AD and AZ, are congruent, what's going to happen is these chords are going to be the same length. Now, we're looking at it on a piece of paper from a geometry standpoint, but I want you to consider, even in building things, or even in, I don't know why right now a bicycle comes to mind, but we do need to know how far apart these are in order for us to know if they're going to be the same length. So when we write our theorem, it would say if AD and AZ are equidistant, remember equidistant is just a fancy way of saying equal distance, to the two chords, then the two chords are congruent. So what that would mean is BC would be the same as XY, or the length of BC would equal the length of XY. So for example, if we again were just looking at it from a geometry standpoint, that's a pretty good circle. We're going to look at circle E, and we have AB, we have DC. Notice right away, in order for us to know that it's equidistant, you're going to see the right angles. They are going to tell you that they're congruent. But what we're also going to look at is this whole length here is 3x minus 11, and this entire length here is x plus 9. And we want to solve for x and find AB and DC. So we want to find the length of AB and DC, which means plug it back in. So the first thing that we have to pay attention to is since AB and DC are equidistant to the center C, then AB will equal DC. So you don't have to write all that out, but that's something that, again, the minute you see all those tick marks, you know those are going to have to be the same length. So we're going to go ahead and we're going to take 3x minus 11. We're going to set it equal to x plus 9. And we're, of course, going to solve. So we're going to subtract x from both sides. We're going to add 11 to both sides. And we end up with x equals 10. So there's one of the requirements. Then when we plug that back in, we are going to end up with 3 times 10 minus 11, which would be 19, and 10 plus 9 would equal 19. So AB and DC would both be 19. So not a difficult concept. The issue that I always find with the circle chapter is it does require us to memorize quite a few concepts, and if we don't, then something as easy as just set them equal to each other does become more difficult. So then what we're going to look at is, again, we talked about more segments. So we do have segments or lines that do extend inside and outside. And that's what I want to look at very quickly. So in our first circle, again, circle A, we're going to have a segment that looks like it starts off to be a chord because the endpoints are on the circle, but it's going to extend to the outside. So segment XY is a secant segment. And secant is our next segment that we want to talk about. Contains a chord, but extends outside the circle. So notice one of the endpoints is outside of our circle. So now what we end up with are these other theorems that are going to use all of the segments now that we've talked about. So we've talked about our chords, we've talked about tangents, and now we've talked about secants. And nothing's going to happen with a secant unless it's combined with something else. So our first one that we want to talk about is what's called chord segments. And we're not very creative once we get to this point. It's going to be a combination of two chords in a circle. And they're not triangles. They appear to look like triangles, but remember those parts out here are rounded. But we do have two chords that are intersecting inside our circle. So two chords that are going to intersect inside our circle. And we're going to just go ahead and name those parts W, X, Y, and Z. So if two chords intersect inside our circle, they kind of create what looks like the cross multiplication from our similar triangle chapter. So it's almost like these two triangle type pieces. They're not really sectors of the pie, but they are kind of like triangles. They would kind of create this correspondence like they were proportions. And then when we cross multiply, you're going to end up moving straight down your chords to do the multiplication. So if two chords intersect inside the circle, and I suppose I could have said they're products instead of will multiply. I like to remember multiply straight down a chord, equal multiply straight down the other. So I'm going to just work straight down one chord, straight down the other. So when I look at how this formula is going to look, straight down one chord, that's W times Z, because it's all on chord AB, equal straight down the other chord, that's all on CD. We multiply those two together. Straight down one chord, multiply them together, straight down the other, multiply them together. So then there's going to be two different combinations. Not bad. And we have what are called secant segments. Notice how there's a secant from A to C, but now there's another secant from E to C. So what we're looking at is we have a chord and then we have a full secant. We have a chord and we have a full secant. So when that happens, this is called a secant. Notice the abbreviation. Secant segments. And the easiest way to memorize this is you're going to take the outside times the full length. So outside BC times the full length AC. And we're going to do the outside times the full length. And that's because we have our intersection outside of the circle. Outside times the full length, outside times the full length. So if I was to write this out with what it looks like up here, BC times AC, and then DC times EC. And that's with our secant segments. Now we do have another combination where we're going to end up with a tangent so AB is a tangent. It touches only at one point. But we are going to then take our secant. Notice it does cross again. But it does still connect outside of our circle. So again, even though this one is called a secant tangent segments, they still touch outside of the circle. So they're going to actually follow the exact same pattern. Outside times the full length, outside times the full length. So on this side, we do have outside BC times the full length BD. And on this side, we're going to talk about the exact same thing. Outside AB times the full length, which also happens to be AB. So sometimes what you find is it'll look like this where it's squared, because remember, anything multiplied by itself is something squared. But again, it's because both of these fall outside of our circle. So we've talked about already, if you remember, last time we did have that last combination where we talked last week about what happens when we have two tangent segments. And with our two tangent segments, they do both, again, intersect outside of our circle. But with tangent segments, they're going to be equal. And it actually still follows this pattern. Outside times the full length, outside times the full length. They just end up being equal to each other. So these will always be equal. So we have our secant segments, outside times the full length, outside times the full length. Our secant tangent segments, it is still outside times the full length, outside times the full length. And we do have tangent segments where they just appear to be equal. The only one that's different, and that's because it's all inside our circle, is here, where you multiply straight down and you multiply straight down. So let's take a look at just a few examples and then we'll be done for today. So our first one, let's go ahead and look at our two chords. I'm going to go ahead and, similar here, talk about 10x, 12, and 8. So we're going to go ahead and we're going to solve for x. And again, what we're looking at is the fact that we do have the endpoints on the circle. Both segments are inside the circle. So when we go to solve, we're going to multiply straight down this one segment. So that's going to be 10 times x. And we're going to multiply straight down the other segment, which is going to be 12 times 8. So 12 times 8, it's going to be 96. 10x equals 96. So x is going to be 9.6, which is 9 3/5. And that's it. When we look at a secant situation, make this guy go this way. So A, B, C, D, and E. Let's make this guy 12. This one looks smaller, 8. This one will make 14. And I want to figure out what BC is. That's X. So again, we're going to solve for X. But I want to follow the same pattern. So when I start my work, why not label the whole thing Y, or just again follow the pattern? Outside times the full length equals outside times the full length. Well, the outside over here is X. The full length, we would have to add those together, and that's going to be X plus 12. So I'm going to multiply that by X plus 12. And then over here, outside 14 times the full length, we're going to have to add those together. 14 and 8 is 22. And we're going to multiply those together. Now what ends up happening here is this is where we have to remember, in some situations, this is going to be a pretty easy question. Maybe it was the fact that the outside here, we had a value and we just wanted to figure out what that full length was. So it could have been that it was pretty quick, but here we have to remember that when we distribute, we're going to end up with what looks like a quadratic. And the minute you have something squared and something to the first power, you got to bring everything back to the same side, and then you have to solve by either factoring or using the quadratic formula. Now, I don't happen to know the factors of 308 off the top of my head. And as I'm looking, I'm going to take what I think is the easiest path, and we're going to plug this into our quadratic formula. Remember, A is the value in front of X squared, B is the value in front of X, and C is the constant all by itself, and that's a negative 308. Our quadratic formula is negative b, plus or minus means there's actually two parts to this. The square root of b squared minus 4ac all over 2a. So we're going to plug in negative 12 plus or minus 12 squared minus 4 times 1 times negative 308 all over 2 times 1. So we have negative 12 plus or minus 144. Now a negative times a negative is a positive. 4 times 1 times 308 is going to be 1232, all divided by 2. Now I added those together, and negative 12 plus or minus the square root of 1376 all divided by 2. Now I'm just going to check to see if 1376 happens to be a perfect square, and it's not. So I am going to check if 1376 is divided by 4. It is. It's also divided by 4 again. All right, so I know that this can be divided by 16. So if I wanted the perfect answer, negative 12 plus or minus, this guy simplifies into 4 radical 86 divided by 2. Again, all I did was simplify. This was 16 times 86, so 4 radical 86. And I'm going to divide both values by 2, and I end up with negative 6 plus or minus 2 radical 86. Now, negative values for x probably aren't going to work, so what we are going to want to do is, instead of leaving it as a exact value answer, which doesn't show us positives or negatives very well, we're going to go ahead and we're going to take the square root of that 1376, and that's 37.1-ish. We're going to add that negative 12 because one of them is adding, and we're going to divide by 2. And we find that x is about 12.55. Now I'm also going to take the square root of that 1376, but what I'm going to do is I'm going to make it negative. So how about we start with negative 12 minus the square root of 1376. That's going to be a negative number, and we're going to divide that by 2. And already I know this can't be possible because what I'm trying to get to is a length for x. I can't have negative lengths. So because I can't have negative lengths, this one isn't going to work. So when I do have my final answer for x, my final answer for x could be, if they wanted the approximate value, 12.55. If they want exact value, I would put, even though it looks negative, negative 6 plus that 2 radical 86, because that was where it was positive. So again, this is our approximate answer. This is our exact answer. Now again, this problem could have been a lot faster had simply our unknown been placed somewhere else. So let's just take a look at a different one. We're going to look at our other combination that we've not looked at yet, and that is our secant tangent. So here's our secant segment. Here's our tangent segment. And we're going to go ahead and say that this out here is we're going to say that the whole thing is 36 meters. We'll figure out what that one is. And we'll go ahead and say that this one is 24 meters. And we want to solve for x. Now again, obviously we have so many different combinations that we can identify how to set up or be given combinations of where these numbers would fall. But again, what we're looking at is it falls outside of our circle. So just like before, outside times our full length, outside times the full length. So outside over here, we need to recognize that if the whole thing is 36 and that part is 24, To get the outside, I'm just going to subtract, and I find that that's 12. So outside 12 times the full length 36 is equal to outside x times the full length x. They just happen to be the same. So 12 times 36, you can see, is 432 is equal to x squared. Now, in order to solve, we know we have to do the opposite operation, and I'm going to take the square root of both sides. Now, kind of use your hints up here. We already know that one of the factors is 36, and that's a perfect square. But I also see that there's a 4 hidden in here. So I'm going to use my, I guess, context clues to take a look and say, well, what's 36 times 4? So what we just found out is that the square root of 432 is really 3 times 144. And if you're not sure, take 3 times 144, and you end up with that 432. So again, 4 times 36 was the 144, but remember 3 times 4. So I'm using, again, my context clues. So when we simplify, 144 times radical 3 would be what we're looking at. So if I want my exact value answer, 12 radical 3 would be what x is. If I just want the rounded answer, just plug it in, square root of 432, and we end up with an approximate value answer, depending upon where they want you to round, of 20.78. So just to sum this up, segments of circles, we had chords. Don't forget a diameter is a chord. We had tangents, and we have secants. The theorems that go with them we already talked last time about our diameter. So again, it has to go through the center. When it intersects a chord, there's our chord, the endpoints are on the circle. If it's perpendicular, it will bisect the chord. So that was our first one that we looked at. We also right away talked about our two tangents that intersect outside our circle. And if they were both tangents, these guys would be equal. Today, we said, let's go a little bit further, and we talked about if two chords were equidistant, again, there's that right angle, and there's the congruent to show equidistant, that these two chords would be congruent. So to make it a little bit easier to see, AB would be equal to CD. So we have two different ones so far with chords. We brought in another one that had to do with chords, where we said if they two chords intersected, I don't know why I keep drawing them on this side of the circle as well. They can be anywhere. We did talk about X, Y, W, and Z that we would multiply straight down, x times y would equal w times z. And then the last two we talked about were what happened if we have two secants that intersect. Even this guy who barely crosses. You can see the little gap there. M, N, P, Q, R. Again, this one falls outside of the circle. So we talk about outside NP times the full length MP would equal outside QP times the full length RP. And last but not least, we'll squeeze this guy in here. We talked about what would happen if we have a tangent secant. And it's the exact same thing. Still outside times the full length. So GH times GH, or GH squared, equals outside HK times the full length HJ. So that is every combination of what we could take a look at with just the segments of our circles. You obviously can go to your Connect Ed book and you can take a look at these. I am also going to, with these notes, upload additional notes that I have found from last year, so you can see a lot of different examples, a lot that you'll notice don't have to worry about quadratics. So you can take a look at those as well. And then when we come back, the next time, I did promise that I would continue to add information, even though I know we're finished tomorrow. I did say that I wanted to make sure that you still had information for next year with circles, so I will continue to add notes and probably some videos, so you can check these out when you want to. Otherwise, just make sure you continue to look at all of your homework and you continue to get everything into me before the end of the day tomorrow. So I hope you guys have a great day. Almost there, but again, I will continue to add things as we go throughout the next couple weeks, and anything that you need. Any questions on past material, anything else I can provide you, just email, and pretty much I'll be here all summer, so please feel free till Wednesday, but you may see another video tomorrow just because. So talk to you soon.